Okay, I was just looking at the exam. There are, for the chapter 5, we have these 3 chapters, chapter 3B, chapter 4, and chapter 5A. You're going to see, let's see, 5 or 6 questions, I forget. Oh, no. There are like 8 questions, 13 questions, and 5 or 6 here, I forget, something like that.
12 and 5 are good.
Well, 12 or 13, I think they're 13.
Yeah. So when I did the quiz for the last one, they had some that wasn't covered, so I'm like getting, it's like some kind of like.
Okay, I'm sorry, I might have made a mistake in that. If that's the case, just shoot me an email. I'll take a look at the quiz, okay?
So can you like specifically, like it's just the only problem that we did?
Yeah, I can look at all of your attempts.
I got it.
Okay. All right. And looking at the test, I think y'all are going to be okay. Okay.
It said it was hard, so.
Well, yeah. But I think you're going to be okay. All right. I can do a quick review, and then we can start looking at problems. How's that for y'all? Okay, so chapter 3, is just on projectile motion. You need to know those basic projectile motion problems. We work several. Like, for example, where you have an object that just comes out with a horizontal velocity, where the velocity in the y direction initially is 0, and then it increases with time. In order to find the time that it's in motion, so to find t, you say y is equal to 1/2 a t squared. You lose the v naught t term because v naught y is 0 in this case. This is just like lab, just like shooting a little ball off the thing. So you solve this for t. Being careful with your signs, remember your y is negative as well as the acceleration is negative. And once you solve for t, then you can solve for stuff like the range. So the range would be vx times t, where vx is just whatever the initial velocity is. Okay? I think y'all are okay with that, right? I think y'all are probably okay with most of the basic projectile motion problems. Nothing real hinky or whatever. It's going to be pretty basic, straightforward projectile motion problems. Likewise, you need to know how to do this problem and various forms of it. I say various forms, just, the things that we ask for in this, where if I have a projectile that comes off with a certain v naught, a certain initial speed with a certain angle, you need to be able to find the maximum height, y, you need to be able to find the maximum range, x. In order to do that, the basic idea is that you first find the time. To do the time, you're actually finding t top, right? That's half the total time, where you say vy at the top is equal to v naught y plus ay times t. That's 0 is equal to v naught sine of theta plus ay t top. Y'all okay with me not putting numbers in right now? We'll get to some problems, just sort of laying out the basic idea for these. Yeah, okay? We'll do some with numbers in just a bit. So then you solve this for t. Remembering that that's half the total time. So the total time equals 2 times t top. So here, at this time, if I'm looking at time, this is t top, and this is twice t top. So then I could ask a couple things. To find y, I would say it's v naught y times t top plus 1/2 ay t top squared. Right? I use t top because that's the time when I'm at this point, at the highest point in the trajectory. And then over here, if I want to find the range, I just say x is equal to vx times t. Where vx, remember, that doesn't change throughout the trajectory. That's just going to be v naught cosine theta times twice t top. That's our total time because I'm finding the position after all the time has elapsed. Okay? Those are basic projectile motion problems. You should expect to see one or both of those. Rhea?
Can you go over like the rules more, because like sometimes on the practice test it's tricky because of the wording, like
The rules.
yeah.
Like the rules of
Yeah, can you, like, for example, like the the acceleration is like negative 10, there was like questions where
like a conceptual type question.
Yeah.
Yeah, you need to remember some things about projectile motion. Let me just sort of try to summarize those. You'll see several, I mean, of these 26 questions or whatever, there are probably only a third or maybe a little more than a third are actual calculations. So there are a lot of conceptual questions. To study for those, I'd study through the notes and study through the old tests. You'll see a lot of conceptual questions there, as well as those concept tests. But just some basic information about projectile motion. The acceleration in the x direction is always 0. The acceleration in the y direction is always negative 10, and that doesn't change. And so if we look at our trajectory, because of that, we have some things that go on. The velocity in the y direction is initially big and positive. It gets smaller with time, and it goes to 0 at the top. Then it gets bigger, but in the negative direction. So at different times, like here and here, the velocity in the y direction is equal in magnitude, just opposite in direction. Similarly, for the velocity in the x direction, since this is 0, that velocity does not change, so it just goes along the entire time like that. I don't know, what's some other stuff? Well, this is a parabola, a shape, and that's because of, well, it's not directly because of this, but you can think of it because I have this quadratic function, 1/2 at squared, and you can think of that as being like a parabola. It's a little more complicated than that, but let's see. I think that's about it for projectile motion. Oh,
They had one, that was the one you went over like today in class. It was that question of a projectile motion concept, and like E was the really tricky one because like I don't know, something with the Y and the X is not the maximum height is 0. I don't know that one.
Oh yeah, so what is we have some dependencies on things. So for example, the time, the hang time, I like to call it, how long it's in the air, is only dependent upon the y motion. Right? It's not dependent upon the x motion at all. Right? That is completely independent. However, the range, the x range, is dependent upon what happens in the y direction. Because the range is x equals v naught x times t, or x equals vx times t. So since the time is dependent upon what happens in the y direction, how high it goes, right, then this time is also related to the x range. So the range is dependent upon what happens in the y direction. That's why we usually start out by finding the time if we don't have that time. All right. There was one thing you might see this. I'm not sure if you're going to see it, but we haven't directly talked about this, but I think you should be able to figure it out. That if I have a trajectory that follows this path, you know, this is half the time from the top. This is 1/2 the total time. However, when I'm looking at half the height, right, this is half the time. It's also half the total x. However, if I'm looking at half of the maximum height, half of y, this is not half the time because it's a quadratic function. That's actually less than half the time, because if I think about how my y versus t, that function looks like this. If I think about, this is my halfway point in the y direction. notice that it hasn't gone very far at the time. It actually moves more slowly initially, and then it speeds up. That's not right. That's not right. Is that right? Doesn't matter. Doesn't matter. So, I'm sorry. I'm kind of tired.
It just hasn't gone that far.
It just hasn't gone that far, right? So, whereas in the x distance, you will see this actually, in the x range, at the halfway point, half of the time has elapsed. However, in the y direction, at the halfway point, in the spatial direction, at half of y, has not been half the time. It's actually something different. Okay? Y'all follow what I'm saying about that? Okay. All right. So let's look at that sort of projectile motion in a nutshell. We'll have Newton's laws. You'll need to know sort of basic stuff about the law of inertia, the law of acceleration, and that law of action-reaction, the first, second, and third law, and just be able to identify when they're applied in various places. You also need to, of course, know how to apply Newton's second law, and that you'll have, I don't know, 4 questions on that maybe. You have an inclined plane, of course. You'll have an inclined plane where you have to do the equations, where I give you a list of equations, and you have to tell me which are correct or incorrect. We can look at one of those. You'll also have a dynamics problem, probably something like the elevator problem, like we've worked a couple times in the homework or in class, where you have an object either hanging in an elevator or you have an object that's sitting on the floor of an elevator, and I ask you what is the normal force or what is the tension, if this object is moving up or is it moving down, is it accelerating or not accelerating, that sort of thing. We can work through some like this when we get to the old test, but you'll see stuff like that. You'll also, as I said, see an inclined plane, where you have an object that sits on an inclined plane, and I ask you something about it. What's its acceleration? What's the frictional force required to hold it up? That sort of thing. Remember, on the inclined plane, you need to remember a couple things. Always draw your coordinate system like this. Always draw your weight so that it points down. That's your weight. And your normal force so that it points perpendicular to the surface, so along the y-axis. And then remembering that if this angle, for example, is 40 degrees, and this angle is 90 minus 40 or 50 degrees, and it's that angle that we'll use. All right, so again, with your inclined plane, you should be able to just look at it and say, well, this is FW cosine 50, and then this is FW sine 50, and then fill in whatever forces you have otherwise. You'll also likely see some problems like we did, I think we did one in class today actually, where you have a, we're all in class here, aren't we? Are all of y'all in class students? I think you are, yeah. Where, say you have an object with a force that is pulling up, then what is the normal force? So if this is my angle theta, what is the normal force? Is the normal force going to be bigger or less than the weight here? It's going to be less, that's right, because I'm pulling up. It's like I'm taking away a little bit of that normal force. You can see that if you draw your vector diagram. Here I have the F sine theta. Be careful, because even though with the inclined plane, we do this funky 90 minus bit, we don't do that here. We just use the angle as it is, right? So we have F sine theta. This is going to be F cosine theta. This is our normal force, and then this is our weight. So here, our normal force will be the weight minus this. Our normal force will be Fw minus F sine theta. And if you wanted to find the acceleration, you would just say this force is my force and divide it by the mass, because F cosine theta is the force that acts in the x direction. All right. I think what else was there? There is some friction on there, but there's not a whole heck of a lot of friction. I was kind of surprised by that. It's like, oh man, put that much friction on this thing. So that's good. But there is some friction, so just like Sam. So you will need to know, sort of the basics of friction, how to find it. But it's not like overwhelming on the test. Sam?
Yeah, the question about the friction is like the only
Well, there will be some friction, but not. I think there are just like 2 questions about friction. So not a whole lot. But just remember that static friction, well, first our general formula for friction, which you just need to memorize, and you will have to use it, is that friction is equal to mu times the normal force. That's true for both static and kinetic. So we just put a little subscript for whether it's static or kinetic. Yeah, that's it really. Don't forget that whole thing with the static friction where it's sort of a range up to the maximum.
So what is the difference between static and kinetic?
Okay, good question. So static is when it's stationary. So static means if an object is stationary, then that's the frictional force that's applied. Kinetic means moving. So, kinesis. And if the object is sliding across something, then that's kinetic friction, whether it's moving or not.
So they can't be both at the same time.
They can't be both at the same time, correct? All right. And then that's it for chapter 4. Chapter 5, it was just work. You'll have one where you just have to use this formula to calculate the amount of work. Be careful because there'll be some other numbers thrown in there, not all of which you'll need, so try not to be misled by that. Some stuff where, like relationships, where we talk about, well, what happens if you go twice the distance, or if you go 4 times the distance, what happens to the work? Well, if you went twice the distance here, you just get twice the work. I expect almost everybody to get all these. All right, there are like 5 problems. I want y'all to get those. Those should be easy ones. So you have one of those. I think there was like a conceptual where I asked you, if I change the displacement, what happens? Okay. And then also positive and negative work, and just being able to identify where positive and negative work is. Don't worry about what that means right now, but just be able to identify that, for example, if I have a force in this direction, a displacement in this direction, of course that's positive work. If I have a force that's acting in this direction, a displacement in this direction, that's negative work. And I can also have this where I have a force that is partially in this direction, and then a displacement that's in this direction, then that force is doing positive work as well. Actually, only a component of that force is doing positive work. The x component is doing the positive work. The y component is doing no work at all. Any vector, we can split into 2 pieces like that. And then, I forget if it was work or if it was force, but one of those I asked for the basic SI units. But those should be pretty easy, right? So F equals MA, work equals force times displacement. The cosine theta doesn't have a unit. And I just put in the SI units for each of those. So MA is kilograms meters per second squared, and then this is going to be kilograms meters per second squared times meters. So it's kilogram meters squared per second squared. Don't try to memorize those. I mean, you need to know the equation, so just plug in the appropriate units when you see that question. But you have one of those. I forget if it was work or force. I don't forget. I'm just not going to tell you. Okay? That's it. I think actually, like when I was looking back on the test, the other day I thought it was really hard, but today I'm feeling pretty good about it. All right? And then there is an extra credit question. It's worth a full question, so I think that's about 3.8 points. But you have to get the answer exactly right. Okie dokie. All right. Let's see. I'll look at some old tests. Anyone have any particular questions? Brooke?
Can you do like an incline plane where it has like the weight and like you have to decide whether it's like going up or going down?
Oh yeah. Where you have to decide if it's going up or.
I know about one quizzes and I was like, I don't think we need to do this in class or anything.
You had a force acting on it?
Oh yeah, what does it take to like overcome a static friction to move or something?
Is that what you mean? Like, how much force does it take to overcome
I'm
it?
just if I could find.
Okay. All right. While you're looking that up, any other questions? Any particular questions about stuff or particular sticky points?
Incline planes that are kinetic the static friction.
Okay. All right. Courtney?
I I was doing number 10 on fall 2008, exam 2, and I was watching like the video after, and it said like the sine was on x axis and the cosine was down.
Yeah, you gotta be careful. What question was it? 10?
Yeah, number 10.
Because used to, guys, I will come back to your questions, but let me address this right now. Used to, I would sort of, is this the one?
Like, like whenever you did the video, it seemed so complicated, but all I did was took the force going that way. And,
Yeah, it's not really that complicated. If you go through all those steps.
yeah, I just did it like, and I got the right answer. When I watched the video, it was confusing.
That's my job, is to confuse you. All right, so yeah, really, I mean, you're going through all those steps in your head. So hopefully you're to the point where you don't have to go through all those. Well, I gotta resolve vectors into their components and yada yada yada. So like, hopefully you can just look at this and do a lot of stuff in your head. So let's see that. So here I want to know what's the minimum force if the block remains in place. There is no friction on this. So you would look at this and just say, well, gosh, I know that this force is the x component of the weight. So that's going to be Fw. Let's say this angle is 30 degrees, cosine of 60, right? And that's it, right?
Yeah.
I just say F is equal to Fw cosine of 60. If you realize that you don't really need all the y stuff, and here it's not relevant because there's no friction. Now, if there was friction, you would need to know the y forces and how they're applied. And if you can say, well, I know that if you don't have to write out Fw as a vertically downward vector, and I can just label my x and y components like that, then that's great. That's really the best way to do it. And then it becomes really easy, right? What was the answer here? You remember? 49, yeah. So Fw here was 98 newtons times cosine of 60 is 49. Now, probably on the video, like we did, we drew this, oh, excuse me, and we drew the force weight vector, did all that business, right? And then this angle was 60 degrees, and then we had Fw sine 60 here. We did all of that stuff, but that's not really necessary in our normal force there. And I really like for you to be, especially if you're pre-med, because if you see an inclined plane time on the MCAT, which you could, you just need to be able to do it quickly like that. All right? Brooke, did you figure out what problem?
Yeah, it's question 19 on last year's test.
Okay. Is this okay? Clear on this? Is this?
Confusing.
Okay, I'm sorry. I think going through all those steps is good, but once you get it, you don't really need to see it all. Okay, which one was that, Brooke?
Last year's test 2, it was question 19.
Okay, so a rope is block of 10 kilograms. What is the rate of the acceleration? Oh, okay. So here, we don't know if the block is going up or down. We don't know if this force of 100 newtons is enough to counterbalance or to overcome the force due to weight. So I have 100 newtons here. Actually, you should be able to tell me. Is it going to go up or down? Y'all think? Is that 100 newtons up the inclined plane? Is it enough to overcome the component of the weight? Why is it? Why is it yes? Emily, why is it yes to you?
Because the weight isn't exactly 100 newtons.
Right. What is it?
Well, you have to do the
Okay. It's a component,
sine.
right? Right.
The sine.
So my weight here is 100 newtons, but as Emily said, I'm actually getting only a component of the weight that's acting down the inclined plane. So even though my weight is 100 newtons, see, I'll draw it in red here. I only get the x component of that, which is going to be 100 times cosine of 60. All right, so again, not going through all that business like we've been doing, but I can just look at these two forces because those are the only forces that are in the x direction. And I can say, well, 100 cosine 60 minus 100 is, what's that, negative 50 newtons. That means I have a net force of 50 newtons in this direction. And so the answer then, A is F over M, 50 newtons over 10 kilograms. It should be E. Is that that was the right answer, right?
Yeah.
Yeah. Now again, you can go through all those steps where you draw the coordinate system and label all the forces and resolve the forces into their x and y components. But if you can look at this and just realize that, well, the only forces I have in the x direction are this force and the x component of the weight, then it becomes a very simple problem. You don't have to worry about any of the y components.
What happens if it was the opposite around? Because like that's the common one, but what happens if like
well, right, and we can do it, just change it not to 100 newtons, but let's say that this force was 20 newtons. And then that force is not enough to overcome the weight because this component is equal to 50 newtons. And so my net force in the x direction is going to be 50 minus 20, which will be 30 newtons. And then my acceleration would just be 30 newtons over 10 kilograms, or 3 meters per second squared down the inclined plane. The big question is this force bigger than this force? And if it is, then it's this force that's going to win. Okay? That's a good question. Let's look. There's some other good ones here we can look at for friction. Can I take this away? Like for example here, I have this one where you have a block with a force being applied to it, and we want to know the normal force. Now we've already said, just on if it was just no forces applied to this, or this force wasn't here, the normal force on this block would be same as the weight, which is 100, right? So this has a 100 Newton weight. So the normal force would just be 100 newtons. However, I have this force, so I can write F sine of 30, and then I also have the normal force. So the normal force plus F sine 30. Come on, did I start this? I did, awesome. The normal force plus F sine 30 minus 100 equals 0. And then I solve for Fn equals 100 minus F sine of 30. Now you might be able to just look at this and say, well, this normal force is just going to be this minus this. Can y'all do that? Just look at the vectors now and say my normal force, it would be this amount, but now that I have this force, it's going to be this amount minus this amount. But that's where we get this from Newton's second law, applying Newton's second law. So that's going to be, is that 90? So B is the right answer. And then the next question, so if we have a mu k equal to 0.1, what is the acceleration equal to? Well, if we have mu k equal to 0.1, then I have a kinetic frictional force here. That kinetic frictional force is equal to mu k times the normal force, which is 0.1 times 90, so it's 9 newtons. And I have another force over here that's 20 cosine of 30. Those are my only forces in the x direction, so I just say 20 cosine 30 minus 9 newtons. Oh, this is going to be problematic, right? because this comes out to be 8. Oh wait, no, I'm sorry. 17 minus 9 equals 8 newtons. So it's going to be, my acceleration then is F over m, which is 8 over 10, or 0.8 meters per second squared. Those are good questions. You'll see questions like that. Rhea?
How can you determine why kinetics always on to the left direction? Like,
Well, it's always going to be opposing the motion. So
okay.
and in this case, the question told me on the next question down, it said that it's moving. So I'll just take that at face value. And because the only force that I have is to the right, then I know that it's going to be moving to the right, which means the kinetic friction will be the opposite direction to the left. Always opposes the direction of motion.
Even
For
for static.
static, it always opposes the intended direction of motion, like what direction would it tend to move.
Like if the force is given, then the kinetics formulated. Like.
Right. Yeah, so for, like, a good example of that is the inclined plane. With the inclined plane, you know, you have your x component of the weight going down in that direction, and so the static friction is always going to be opposite that. Now it could have been, you won't see this in your test, but it could have been that this force is actually smaller than the kinetic frictional force, in which case kinetic friction wouldn't function there, it would be static friction. Because this force has to be bigger than this force in order for it to move. And you have to have motion in order for kinetic friction to be relevant. Okay? These are all great questions. Like you'll see questions similar to these. Y'all are good with these? You feel comfortable? I could give these to you right now, right? You could do them? People always smile when I say that. I think it's because they say, yes, I feel great about this. It's like we got this cat, and I hold the cat. And you know, cats, when they get annoyed, they sort of twitch their tail, which is the opposite of what dogs do. And so whenever I hold the cat, and like I'm rubbing his belly and stuff, and his tail is switching, I always tell my wife, like, oh look, he's wagging his tail, he's happy. But he's not really at all. Okay. Let's see. Now we're okay on stuff like this.
Did you do 26?
Yeah, so which of these statements about coefficients of friction is true? Which is bigger, static friction or kinetic friction? Static friction is always, almost always bigger. It's always bigger. So the static friction is always bigger. Right, we sort of gave that example in class when you're pushing a big piece of furniture. It's hard to get it moving, but after you get it moving, it's easier to move it. So that's because the static frictional force is bigger. And so for this one, the answer is A, that the static coefficient is bigger than the kinetic coefficient. All right. I think you also had a simple vector addition. I know we did vectors last time, but it does come up again here, where I give you a couple of force vectors, and I ask you what is the acceleration. So be prepared for that. They're not terribly difficult vectors, but just being able to add up a couple vectors, either on, I think they are both on axis, which makes it even simpler. But you have to do vector addition anyway with the trigs, with the inclined planes. Y'all follow what I'm saying? I give you a couple vectors that are acting on an object, you'll be able to tell me how it's accelerating, or what is the net force on it.
I need a visualize.
I have an object, I have a force in this direction, and I have a force in this direction. What is the acceleration? So, like for example, if this was 2 newtons and this was 4 newtons, the acceleration would be in this direction. The net force would be the square root of 2 squared plus 4 squared, just the square root of 20, whatever that is, 2 root 5. And this angle would be the inverse tan 2 over 4. It wasn't a terribly complicated thing. I remember it being pretty easy. I think you'll be okay with it. All right. take that away. What other questions? You have particular questions?
Could you go over coefficient of friction? How to find that?
Sure. Let's see. So I think there's a question here. On an incline or otherwise? Okay. Let's just do that sort of typical problem we've been doing where we have a static system. So I have a block. Let's say that the mass is, I don't know, 5 kilograms. Let's say that this angle is, I don't know, 20 degrees. And I want to know what is the coefficient of static friction in order for this to remain in place. You'll see this question on old tests. But on this case, it really does help you to draw out all your vectors because you need to know information about the x and the y direction. So I have my normal force here. I'm going to go ahead and draw my x and y components of the weight. So this is Fw cosine of 70. This is Fw sine of 70. And then I also have the static friction. Now I know that from this, I can say that the normal force equals Fw sine of 70. I can also say that the static frictional force is equal to Fw cosine of 70. Notice that I skipped over all that sum of the forces business. I just skipped right ahead to this because this is a pretty simple problem. It's static. I know that these add up to 0. These add up to 0. That means they're going to have to be equal in magnitude and opposite in direction. So these things are true. And then if I want to know mu s, I know that mu s, rather Fs, is equal to mu s times the normal force. So mu s is equal to Fs over the normal force. In class, we've typically been finding the value for these. Students usually find that easier. But notice that I can just take this ratio. I can say Fs over Fw, or excuse me, Fn, excuse me, is just this over this, Fw cosine 70 over Fw sine 70. Those cancel, so it's just cosine of 70 or sine of 70 is 0.4. That's a little bit different than we've completed it in class. You could go through and just find out these numbers, because we know Fw, right? It's 50 newtons. And so you just say 50 sine of 70, 50 cosine of 70, and then do the ratio of Fs over Fn. So anytime you're looking for a frictional force, remember you're going to have to find that normal force too, because they're related. Okay? So 2 or 3 times friction comes up on the test, but it was remarkably not complicated. Like I thought I made it more complicated than it was. But this isn't that complicated, right? No. Okay. Okay. All right. What else? I'll sort of go through some old tests. The elevator problems, you're okay with that? This whole thing, there are some simple kinematics stuff, nothing like projectile motion isn't that simple, but simple kinematics paired with Newton's laws. We've seen some problems, kind of like number 11 here. Is that okay with that? Want me to work through this? Okay, fine. So 10 seconds, you go from 10 to 30 meters per second. I want to know the force exerted. I just need to know the acceleration first. I'm going from 30 meters per second as my final, minus my initial, divided by my total time, which is 10 seconds. Look, this just comes from this equation. A is equal to V minus V naught over T. That's where that comes from. So that's 20 over 10. That's 2 meters per second squared. That's my acceleration. And then I want to know the force. That's just F equals ma. Here's my mass. Here's my acceleration. So it's C is the right answer. Pretty simple, right? You'll see some very simple stuff like that. But it's only simple if you know how to do it, right? If you don't know how to do it, then it's not that simple. But, here's one where you have two ropes. Oh no, that's something different, I'm sorry. Y'all holler out if you see anything that you want to look at. Y'all are clear on this. We went over this in class. It's number 6 about the acceleration. The acceleration is always down. Right, this is the acceleration. But remember, the velocity is a little bit different. In the velocity, you have your vectors that have both x components and y components. It's initially 0, but then it gets bigger and bigger, and so the net vector is going to be something like this, or something like that. That's for the velocity. The acceleration is always pointing down, but the velocity sort of changes with time. The net velocity, the total velocity vector. There's projectile motion problem. That's like the one we worked before. No, we're not going to see any vector stuff like that. All right, let's see. Y'all can tell me right off what the normal force is on that? Or did we do this one already? Okay, yeah. Remember, it's just 10 or 100 sine 60, right? 100 sine 60 is our normal force. It's the y component of the weight. Basic SI units of a Newton. In this case, if I want to know the magnitude of the force, it's just this one is a little more complicated. I have this object. It has two forces, F, Fw. And so I'd say F minus Fw equals the mass times the acceleration. So F is equal to Fw plus the mass times the acceleration, which is 100 plus 100 newtons plus 10 times 5, which is 50 newtons, which is 150. All right, that's sort of like the elevator problems that we did in class, where you have an elevator moving up or down. Okay. You'll see some problems like this. Go through the concept test where you change the force or you change the mass of an object. How does that affect the acceleration? Similarly, you see some stuff like this, how the normal force is affected. You could see one like this. You won't see one with different angles, but you could see one like that. That's it on that one. Any of these stand out to y'all? Number 8? Okay. If you do see one of these, just remember that the tension on both sides are the same, right? Because of the symmetry with the angles. And then I have two y components here. This is going to be Ft sine of 50, Ft sine of 50, and then I have the y component of the weight, or the weight rather, and so I just say 2 Ft sine 50 equals the weight. Now there's a whole other thing that we sort of left out, where we have the x components, Ft cosine 50, Ft cosine 50, but because I can say that this is equal to this, because it's stationary in the x direction, then I can further say that this, Ft on the left side, is equal to Ft on the right side. So this just tells me that my two tensions are the same. That should be sort of intuitive to you, because these angles are the same. Hopefully that's sort of intuitive, that those forces are also the same. And then I just solved this for Ft. 230 newtons over 2 sine 50. You had a homework problem basically identical to this. Emily?
Can you kind of explain why inclined planes are the only scenario where you 90 minus
Yeah, sure.
the angle to get the component.
Yeah, it's just because of the geometry of it. It is the only scenario, though, because if I have my weight down here, it's really how we choose to draw our coordinate system, because we're drawing our coordinate system like this along the plane, and so this angle, if this angle is 40 degrees, then this angle, which is from the x-axis, is going to be 90 minus 40, or 50 degrees. See, because I have a right triangle right here. And you don't see that on any of the others. Like here, for example, on this problem, this angle is 50 degrees, and this angle is also 50 degrees. Because you have two parallel lines, you have a line that crosses across them, so these two angles are the same. Likewise, when we had the problem where we had like a force like this, well, there the force, it's a lot simpler because your force is just measured from the x-axis, and so you're going to use that force. The point is you always want to have your angle measured from the x-axis. Does that clear up a little bit? It's because of that right triangle that we have right here. That this angle is 90 minus the incline. It makes life a lot easier if you just do that. All right. Okay, let's kind of close this one. We'll just go a couple more minutes, if that's okay, unless you have any particular questions. You just want to wrap it up right now?
Yeah, it's fine with me.
It's fine with you? Okay. All right, let's just wrap it up then.